This is the second video for environmental systems concerning the NAAB compliance pages that are part of our final deliverable. In the first video, I said that I was going to cover the building performance page and the environmental control systems page. I did that, but I realized I needed to say some more about the environmental control systems page, the HVAC page, so I'm going to do that in this video. The first thing to point out is that even though we're only designing an HVAC system for one zone or a related group of zones, we need to define the entire project as thermal zones. So as a reminder, a thermal zone is simply a box of air that's separated from outdoor air, the ground, other zones, and it's defined by the number of people it has in it, the amount of activity, the amount of equipment, it's facing toward the sun, the amount of wind that's blowing against it, etc. And all those variables will determine a certain amount of heating, cooling, and fresh air that zone needs, and that will define it as separate from another zone that's next to it or involved in the building. So I am using the little Jim Charette project that we did at the beginning of the semester here. I decided we'd have 5 zones for it: corridor, office, lobby, mechanical, locker, and gym. I defined these first by their occupancy. They all have different occupancies. And we know that from what those would be by looking at the code. So I can go to the code, 2024 IBC, just put that into your browser, go to chapter 10, means of egress. 1004 is occupant loads section. And here we find the chart that tells us the amount of either gross or net square footage per person allowed in a specific zone type. So for example, if I come down to locker rooms, I get 50 gross. That means 50 square foot per person is allowed in a locker, and we'll see that's what I put here. And so the gym has a lot more people because there's more activity there. Corridor is actually nobody's regularly in a corridor, so we don't have to give it a people designation. We're not going to say there's going to be heat load from people there, etc. So that defines kind of the basis of the thermal zone. And then from there, you can go as far as you want based on your understanding. If you look at my chart, what I did was, even though those are separate zones, I combined them with my mechanical system concepts. And now we're not going to design all these, but I think it's good to describe something in general terms. So for example, I'm in the gym, which is what I'm going to design. I'm going to have a VAV system, that's variable air volume. But I'm going to have really 2 zones. So I'm going to have one piece of equipment for that gym, but I'm going to send a different temperature and relative humidity to the spectators and a different to the court. In the corridor, I'm not really thinking. I'm just going to say I'm passively heating and cooling it. In the lobby and the locker rooms, I am going to, even though they're separate zones, I'm going to use one roof-mounted DOAS. So that's an air handler on the roof with heat pumps. VRF is variable refrigerant flow heat pumps. So I will have different temperatures going to the lobby and to the locker rooms, but from the same piece of equipment. And then the office, I'm going to have it's just a couple people in there, so it's just going to have its own little mini split heat pump and its standalone ERV, energy recovery ventilation. For those other ones, they would all have integrated ERVs into their systems. Okay, so that's kind of my description of my mechanical system for the whole project. I don't have to do anything else with that. I decided to then design the gym mechanical system. So I have a roof-mounted air handling unit that's bringing in the fresh air and dumping out the exhaust. I have an ERV, which is an energy recovery ventilator. I have a heat pump on the roof that is with refrigerant, so it's a VRF. In other words, this is refrigerant here going to the heat exchangers in the air handling unit, and that is going to send different amounts of refrigerant to deliver different temperatures. And then I have return ducts and supply ducts. I can see those more clearly in my floor plan. So the supply is coming down to a trunk on each side, branching off. Then I have supplies going to the spectators and supplies going to the court. I have some supplies over here near the windows because that's going to demand more heat and cool. based on the time of year. And then you'll see here I have VAV boxes that will allow me to send a different temperature here and here. I probably should have put VAV boxes here and here also, so I could just, why not? That would allow me to have a baseline temperature coming from the supplies and then change those temperatures at each of these supply branches. These little squiggly lines here are just returns, so there's just two big returns by the people. That's the full system. I've got a little key up here describing what everything means. I've got an axon over here that lays it out so that you can, you always look at these three together to make it make sense. I just sketched on here because I'm doing this quickly, but for my section, it'd be great if you sketched, as far as I'm concerned. We don't need anything fancy. We just need it to be clear. One thing in this section up here that I did was just to show that this is the bottom of my bottom quarter of my trusses. So I'm basically saying that these are going through the trusses and they're exposed. As a review, I wanted to point out a comparison of the three systems we've really been talking about, and they're very similar. And there's a reason why you would choose one over the other, which is also simple. So this is from Climate Studio. I suggest you, if you haven't already been doing it, use their Climate Studio docs, climatestudio.docs.com page. It's very helpful. And for example, if I type in VAV, I come to the diagram that I'm going to show you, but I also have some settings down here that help me understand how to make changes in Climate Studio if I'm actually running a simulation. Okay, so if I go to these diagrams from that website, they're very clear comparisons. The VAV system, you'll notice, so I'm going to go through all three of them right now. This is the VAV, variable air volume. This is the DOAS, dedicated outdoor air system with fan coil units. This is a fan coil unit. And this is the dedicated outdoor air system with variable refrigerant flow. This is the variable refrigerant flow. They look pretty similar, right? And because they are. So they all have this big box up here. And this is the air handling unit. We're bringing in fresh air here, exhausting stale air. These are blowers, right? The fresh air comes in, goes by the heat exchangers. In the VAV, we have a boiler and a chiller. This is a cooling tower that's probably on the roof. Those temperatures are supplied to the heat exchangers, and so then the temperature is delivered to the zone. There's a reheat here so that we can have a control that's specific to each zone, each room if we want to. And then we have a return coming back. Very simple. I want to point out that there are slides on Canvas that go into more detail about this equipment. So if you don't remember what an ERV is or an HRV, there are slides that go over them. And this is it's just called HVAC. This lecture 3. And remember, so the basic idea of energy or heat recovery ventilation is that we have it. It's hot outside. We've spent money, hot or cold outside. We've spent money getting a stable temperature inside. We've got to take some of that stale indoor air and exchange it with fresh air. Of course, as Professor Theodoridis has said, that's way too simple. But the concept is we have to exchange air, and we have these devices that will allow us to save energy as we do that, and not just bring in 25-degree cold winter air and have to reheat it from that baseline temperature. Anyway, there's tons of other information in these slides that's related to this. But the point here is that the VAV system, variable air volume, generates the temperature differences for the variation in the amount of air you send to the zone. And the advantage of it is that everything is delivered in the air. So you have fresh air, heating and cooling all in the same airstream. That's great. But there's various disadvantages. One disadvantage is that we're using a fossil fuel here. But another is, look, these ducts are pretty big, right? Because to deliver air, temperature through air, it takes a lot of volume. So if we go to a DOAS, dedicated outdoor air system with fan coil units, you'll see it's basically the same thing. We have the exact same air handling unit doing the exact same thing. We've gotten rid of our boiler and exchanged it for a heat pump. And our ducts are really small. Why are they small? Well, because our heat pump. Um, we have two different heat pumps here. Let's say this one's sitting on the roof. It's got a condenser so that we can recharge the system, and we're sending water to a fan coil unit in the room to heat and cool hot or cold water. And there's just a fan in there. That's why it's called a fan coil unit. And these are the coils. They're coils because they have a lot of surface area, so that the air blowing across them has a lot of access to that temperature that's in the water. So we're heating and cooling with water, hot or cold water from the heat pump, blowing it across. We're heating blowing air across it to heat and cool the room. The only thing we're using this unit for now is to bring in fresh air, and fresh air is a lot less volume. We're just talking about this person surviving, so we can have much smaller ducts. So if you have a problem with duct sizing in your project, you can choose one of these systems and alleviate it, because these can be smaller, much smaller, and they can be flexible, so you can snake them around things. We're still heating and cooling because we don't want to bring in really cold or hot air into this room. The only difference with the next system, which is the DOAS, Dedicated Outdoor System VRF, is that we have the same heat pump that's preheating and cooling the air in the air handler. We have another. They just made it a different icon. It's really the same thing. It's a heat pump, but it's delivering temperature with a refrigerant rather than hot or cold water pipes. That's the only difference. Now, the advantage here is that these units, you've seen them a bunch. I'm actually going to go see if I can find them quickly. They're often used for retrofitting. One name for them is mini splits. There's other ways of doing this, but I'm just saying that. So this little unit, this is the thing on the roof that's got the compressor in it. This little unit's got a fan in it, and you feed it with line sets. So this has got a little refrigerant tube for heating and cooling, so supply and return refrigerant and electricity all in one little flexible tube. So it really makes it easy you put this thing on the roof. You send one of these little coiled up line sets. You can snake it around through the building. It plugs into this guy here. When it turns on, this little flap falls down. The fan blows out, blows air across some coils where the refrigerant is. So it's easy to retrofit. So these systems are very similar. They just have very practical differences that make them better or worse for a specific project. For us, it doesn't. It just matters that we have heating and cooling, fresh air with energy recovery ventilation, and distribution. Okay, that's all we need. Okay, the final thing we should talk about is sizing. Now, if you're just trying to get through this and you have a basic level of understanding, your sizing can be pretty straightforward. You can look at the pictures in the slides if you're using one of these units, for example, and just kind of make it the same size. They're pretty big usually. I just kind of sketched this. This is an outdoor heat pump unit. This is a DOAS or an air handler on the roof. And then I made ducting for these purposes that just seems believable. What I would say to you is, if you're just trying to not do any calculations, I would make your ducts maybe 1.5 feet tall and about 3 feet wide, your trunk ducts, and then the branches can be smaller than that. So that would read realistically to me if I were looking at it, and I think that's fine if that's all you can muster for this. We did in my section, and I'm not sure where else it was done. We did go further, and we used this little spreadsheet to create actual trunk and branch sizing. And the way we did that was using in the thermal analysis simulations for what. Let's say we were okay. Here's my where I optimized. This is from the last video. If I go down, not look at the energy flows chart, I look at, there's a peak heating and cooling week chart. If you look at, and remember, we're designing our systems for peaks, right? It has to, even if it's not that often, we have to be able to produce this peak. And so that looks like, I don't know, 55 kilobTUs per square foot per year. I'm sorry, kilobTUs per hour. And then for the cooling, oops, it's here, I think. there's a separate chart, and this is in tons, which is kilobtu's times 12,000. So we have a point is we have a peak heating and cooling load, and so we can bring that into here. This is, you'll note, so this is in tons here, and you'll see that those tons are multiplied times 12,000 to get to kilobtu's. We have set point temperatures. We have, which creates a delta T, the difference between the design temperature and the set point temperature is our delta T. These are things you maybe don't need to know, but any of the blue, if you're using these this spreadsheet, the blue cells you fill in, the other cells auto-populate with equations. And the point is then we can put in those peak loads from our different zones and determine a peak cooling and heating load in BTUs per hour, and then we can take this into this little online duct sizing modeler. We would put in the volume from, okay, let me go back to this because I didn't explain it, because I'm just trying to go through it quickly to remind people who want to use this that it exists. What is happening here is that we're getting a total heating and cooling load that we are cooling load, heating load that we are converting to cubic feet per minute. In other words, the amount of air we need to move that amount of heat, and that comes with a constant that I gave you. Point is, we can bring in this CFM value into the modeler. Okay, I decided to actually slow down for a second, because if you're still listening to this, that means you want to do it this way. If not, just stop listening and do what I said earlier in the video. And I did a video on this, I think, earlier in the semester. But anyway, just for anybody who's interested and hasn't seen it yet, let's go over this. So I'm going to use this, my optimized VRF version. Let's just, though, look at, like, if I'm down here at an energy code version, it's actually lower for the heat load there. Let's see about the cooling load. 6 is a little higher for the cooling load. Interesting. But anyway, so let's use my optimized one for the VRF. I'm going to go to start with heating. I'm going to call that, let's see, 48. I'm going to say that's 58 kilobtu's of peak heating, and I'm going to say we're at, I don't know, 5.5 tons of cooling. So if I come over to my spreadsheet, and let's just see if these cooling design temperature 88. Yeah, that's okay. Yeah, those all seem. I think I would probably go higher, probably 68 with this, and maybe even higher than that. And usually the cool. I think we actually had 75 or something in the simulations we ran. So let's make this 68. Doesn't really matter. I'm just saying. And then what did we say? We said 5.5, and I'm just looking at the gym now because that's all we're designing for. And did I say 58,000? Okay. So these are the totals down here, but we're just looking at this line. So what are we saying has happened based on these sets of what the temperature we're designing for, the temperature we want inside. In other words, this is the outdoor temperature. This is the indoor temperature. We looked at the peak load in our simulation. We got 5.5 tons of peak cooling load. That translates into 66,000 BTUs. It's per hour. And then we had 58,000 peak heating load. And by the way, so this is more advanced, but we talked about it in class at one point. Heating, we need to send temperature that's high. Like, it needs to be above the temperature we're desiring, so 100. And the cooling is opposite. We have to send it below the temperature we're looking for. And so that's going to make a difference in terms of how much heat we have to move. I mean, how much energy we have to move in the air. And the more energy we have to move in the air, the more air we need. So that's this conversion. We go from the amount of heat we're supplying to the amount of air, cubic feet per minute. And that requires this constant about how much heat you can move per degree temperature per hour. Anyway, the point, don't need to understand that necessarily. I'm just saying that, so now we actually have even though our cooling load is much higher than our heating load, the peak, the CFM that we need to move is actually not as much higher. Because in other words, at 66. Wait, I'm confusing myself now. Let's just put it this way. We're looking at the most air we have to. It's moving through the same ducts, so we were looking at the most air we have to move for either heating or cooling. If we were just talking about heating, we'd be moving 1,700 CFM. For cooling, we're moving 4,000, so that's what's going to drive our duct sizing. We take that number and we put it in our modeler. 4,000. These are other. So you got to set the units. I'm going to use flex duct. You have to have another restricting variable. I would just put friction loss 0.1. This is something I got from their help page. This is if we want to limit the height of the duct. We'll maybe do that in a second. I'm going to run the calculation. And you see that we have a rectangular duct, which is about 2 feet by 2 feet. So let's say we didn't. So that's for just for this zone for our trunk duct. Let's say we wanted to limit that, because like I said before, let's say we want to do 1.5 feet. So that's 18 inches. That will make the width of our duct more. So if we want to limit how, because we're talking about it's going to drop our ceiling height if we have to have more ducting. So we could also say, well, we're going to make it wider but flatter, less deep. So that's a control you have here. We take whatever variables we want out of there and put them into the spreadsheet here, and then our branch ducting is automatically calculated from that. And you see here, it's just, well, you maybe can't tell, but it's just the total here times 1.2, so it's 20% larger. And that's because if you think about it, so the trunk and the branches have to move the same amount of air, right? And we have to have the same amount of air being supplied as being returned. So if we have a big, huge duct, it has less surface area to volume, right? So it's going to have less friction. If we take that same volume of air and divide it up into 4 branches, to move the same amount of air, we'll have more surface area around that air, and therefore we'll have more friction. So the branches need to be a little bit in aggregate larger. That's all that's happening there. So if you were trying to accurately, I didn't even do this one yet. So that's even wrong. I don't remember. I don't want to actually do it. I think it was, so we're saying it was about 4 square feet, right? Because it was like 2 feet by 2 feet. Then you would, if you were really trying to figure out your branching, then you would say, okay, off of this trunk, I'm going to have my branch ducts. If I've got 8 of them, they're going to have to then, I get to divide the 4.8 by 8 to see how big each branch needs to be. All right. Again, if you're still listening because you went away for a cup of coffee and came back, this is just for the more advanced. There are people in my section who will do this and have a more advanced understanding, and I'm reminding them how this works. If you don't want to do this, you don't have to. All right, that's it for the environmental control systems page.